Good morning, good afternoon, good evening, wherever you may be in this part of the world. Welcome to another session of my presentation series. And this time, the title of the topic is Understanding the Different Maintenance Strategies for Generation and Substation Assets. As usual, my good name is John Kweku Amotu, and I've been a professional electrical engineer for the past 31 years, and I'm based in the United States of America. Now, let's talk about what is the content of this slide. Okay, so first of all, we'll talk about what maintenance means. What is the definition for maintenance? So maintenance is the application, right, of technical maintenance practice and administrative practice. Administrative practice involves, preparing the cost and also the software asset management software that you utilize basically to implement the maintenance strategies to restore the reliability of the equipment. So that is the definition of maintenance. Now let's talk about the importance of maintenance. So the first one is basically we are extending the useful life of the equipment. So let's get some examples. Let's say substation assets. We have a power transformer, right? We have a circuit breaker, high voltage circuit breaker. We have a medium voltage circuit breaker. We have disconnect switches, right? Okay. And now we have a battery systems with a DC battery charger. Okay. So the goal is, when we are implementing maintenance on these substation assets, basically what we are trying to do is trying to extend the life cycle of the equipment. And another terminology that you can utilize is enhancement of the life cycle of the equipment. So if the equipment is supposed to, let's say, last in operation for 40 years, at least, by implementing maintenance and enforcing maintenance, we can extend it to about 50 years or even more than that, to about 60 years. So that's what we are trying to do. And if, let's say, the manufacturer projects or estimates the useful life cycle of this equipment to be 40 years, right? Okay, so by implementing the required maintenance strategies for the equipment, what we are trying to do is to at least reach 40 years as a minimum. And after 40 years, it could be, we could add some additional number of years in addition to that, based on how successful or how rigorous our maintenance strategies are. Next, maximize the production of the equipment, and that is perfectly true, right? Okay, so basically, if you have a switch here, right, that basically provides power to motors, right? Industrial facility motors. Right? Okay, so if we are able to perform and maintain the maintenance of this equipment, either time-based maintenance, predictive maintenance, or condition-based maintenance, if we have a condition monitoring devices, that the technologies that are mounted on the switchgear, then we are able to prevent failure of this medium voltage switchgear in service. And as such, we are able to provide reliable power, voltage, and current to these motors, right? So basically, we are ensuring the reliability operation of these motors because, if there should be a fault condition because of inadequate maintenance being performed on this equipment, then the medium voltage switchgear can fail whilst it is in service. An typical example is basically if you have a lot of contamination on the insulation system of the bus, right? What is going to happen? Basically, with time, it's going to arc to ground. And if it arcs to ground, basically, you can get a face-to-face fault or three-phase fault to ground, right? And basically, that can interrupt power supply to these motors. Next is budgetary control, right? Okay, so basically, if you plan maintenance of this equipment, at least you have it in your O&M budgeting, This is the amount of money that you have allotted for the maintenance of this equipment. On the other hand, if you fail to implement the required maintenance for this equipment and it fails in service, and I gave you a typical example of how it can fail in service. And another example I can give you is for the circuit breaker, right? If you don't perform the required maintenance on the circuit breaker, a typical example is performance of insulation resistance, performance of a timing test, performance of travel motion tests, and performance of contact resistance testing, right? Okay, so these are all very important testing that is done on the circuit breaker to ensure the reliability of the circuit breaker, right? So if you don't perform all these tests, right, and basically the circuit breaker fails to operate, that is, fails to trip a motor when there's a fault, or the circuit breaker fails to close in, when you want to energize the motor, right? What is going to happen? Basically, you have to shut it down. You can end up, losing the whole box, right? You have to shut it down. First of all, you end up losing productivity, right? Revenue from productivity, right? Then you incur additional costs to repair the damage, right? And you might end up losing the whole switchgear, and you have to basically, replace the whole switchgear, right? You experience an extensive downtime, right? And that is huge loss of revenue. Right? So that is budgetary control. So if you're able to maintain and implement the required maintenance strategy and perform the maintenance on this equipment, you can basically ensure your budgetary control. Next is downtime of the equipment, and I think I explained it in the earlier on, that once you implement all these time maintenance strategies for the medium voltage switchgear, right? Time-based maintenance, predictive maintenance, condition-based maintenance, right? You enhance the reliability of the medium voltage switchgear. On the other hand, let's take an example for a power transformer, right? A power transformer, you can either have a time-based maintenance, right, where every 6 years you take the transformer offline and basically perform all the electrical inspection and testing. The routine maintenance testing results are basically that you can perform is basically capacitance and turn delta, turns ratio, insulation resistance and polarization index, excitation test, impedance test, right? Then winding resistance test. Okay, so this is basically majority of the routine tests that you can also perform on power transformer based on time-based maintenance. In addition to collecting oil samples for DGA and oil quality analysis, right? Oil quality analysis, you can make mention of moisture, breakdown voltage, acidity, neutralization number, interfacial tension, IFT, and etc. etc. Many, just to name a few of them, right? Okay, so what you are doing is basically once you implement all these maintenance testing of all these parameters, you end up basically reducing the downtime of the equipment because you are able to implement enhance the reliability of these equipment. Next is implementing and reducing operation and maintenance costs, and that is perfectly true, right? Okay, so like I made mention that if you are able to implement all these maintenance strategies, right? Okay, for instance, if you implement a condition-based maintenance, right, where for instance a transformer, you have a bushing monitoring device, right, that basically provides a real-time basis the bushing monitoring parameters, that is capacitance and tan delta of the C1 section, capacitance and tan delta of the C2 sections, then the leakage current and the wattage power loss or not due to leakage current flow, right? Then you're also able to install a condition monitoring device that basically provides oil quality parameters to include moisture, then DGA, right, on a real-time basis. Then also, if you have an OLTC, you have an OLTC condition monitoring device that basically provides monitoring parameters like current, voltage, contact wear, contact resistance, then the current that is being drawn by the motor, and also the motor torque, right? Okay, so based on all these, you can extend the time-based maintenance period for the power transformer from a 6-year maintenance period to, let's say, 12 years maintenance. Okay, so if you're able to do that, what are you doing? You're able to basically save costs, because taking the transformer out of service, first of all, you wouldn't be able to provide reliable service to customers. For instance, if it is critical customers, it means that you have to basically divert and feed the customers from another feeder, right? And you end up overloading another feeder, in addition to labor and cost of labor, and also cost of materials, right? And also, you could use the time that you are utilizing to perform this maintenance on this power transformer on another asset, right? So basically, optimization of resources. So implementing the required maintenance strategy helps to reduce basically operation and maintenance cost, like I made mention. Next is improving inventory control. Yes, because once you are able to strategize and basically implement the right maintenance strategies out there, then basically you will basically take a critical look at your inventory, spare parts, right? So that parts wouldn't be on the shelf for a longer period of time, right? Okay, it means that you have a plan in place where a part will be ordered when you need it, right? Not that a part will be ordered and it's going to be sitting on the shelf, right? So you will minimize the amount of cost associated with your inventory. Next is improving the power system efficiency and equipment, right? And that is perfectly true, right? Okay, so if you're able to implement the required maintenance strategy, what do? You end up basically extending the useful life of the equipment. You end up extending the reliability of the equipment, right? So that within the power system network that this equipment is integrated, then basically you improve the efficiency of that power system network, and also the equipment utilization efficiency. Yeah, because the equipment will be always be available for utilization. Next, let's talk about what are the criteria that are implemented that basically maintenance engineers, discipline engineers take a look at to select the right type of maintenance strategies, right? Okay, so the first one is the criticality of the asset. That is very important, right? Okay, so what maintenance engineers, what operational engineers do, what foremen do, and what field engineers do, and other discipline engineers do is to select the right maintenance strategy as part of implementation of asset management for high voltage substation equipment, is to identify the criticality of the asset. For instance, if you have, let's say, 3 or 4 power transformers, right? And let's say you have 2 power transformers in this substation. You have 2 in this substation, right? And these 2 are feeding critical customers, right? That should be very important to you, right? That means that the reliability of that power transformer is number 1 on your list, compared to this substation that has the other 2 power transformers, that is power transformer 3 and 4, right? So you will rank these as number 1 and these as number 2. Next is the consequence of failure, right? Okay, so you take a look at the consequence of failure. Okay, if there should be a failure of these power transformers, what should be the consequence? Okay, losing critical feed to customers, right? Loss of revenue. Customers are going to be unhappy, right? Okay, if I lose this power transformer, is it going to affect other equipment that is in close proximity that is being fed by these power transformers? Next is the environmental piece. Is it going to result in an oil spill? And the cleanup of the oil spill, that is also additional cost, right? And if you don't clean it well, it can end up in environmental violation. Right? Also, if there should be a failure and you have personnel working in close proximity to this equipment, what can happen? It can create a hazard that can be basically get a personnel injured. So these are some of the consequences of failure that you have to consider. And if basically power transformer should fail and the oil spill, that if it should catch fire, it can end up basically extending that fire to other equipment that are in close proximity to this power transformer. So this is a typical consequence of failures that basically you take a look at and be able to rank these. Okay, so for instance, if all these consequences of failures criteria that are listed, if this basically is high, then basically you rank this transformer as number 1 and this as number 2. Next is the economics of failure. Economics of failure is first of all cost to replace, downtime, loss of revenue, right? Loss of critical customers, unhappy customers, right? So those are some of the economics that you basically have to consider. Then you can rank it. Next is redundancy. Okay, so you take a look at the setup, the configuration of the substation, right? Is there any redundancy, right? Okay, so let's consider 2 power transformers, right? Feeding a double-ended, switchgear, double bus with a tiebreaker, right? Okay, so here I have redundancy in this configuration, right? Okay, so if I have to take this transformer out of service, right, then I'll have an n-1 configuration, right? That is removing one of this power transformer out of service and transferring all the bus load onto this one transformer and closing the tiebreaker, right? Okay, so there's something they call make and break. So you close the tiebreaker first, then you de-energize, you trip this incoming breaker. That's basically the switching sequence that you implement. Okay, so for you to do that, right, it means that you have to look at the condition of this transformer. Is this transformer able to support all that load? And sometimes you have to take a look at summer peak loads, right? Okay, so these are some of the conditions that the criteria that you consider in terms of redundancy, right? And be able to select the right maintenance strategy. So, for instance, if this transformer, the condition is very good, DGA, electrical testing, inspection, and basically, infrared thermography testing and survey, predictive maintenance survey, and so I can say that, okay, then I can take this transformer out of service. I can give it basically time-based maintenance or condition-based maintenance, and when it is basically I put it down for time-based maintenance at a 6-year interval, it means I can confidently take this transformer out of service and transfer all its load, right? On the other hand, if I extend it to 12 years based on the condition of this transformer, right, then at the 12-year mark, I can take this transformer out of service and transfer all its loads to this one. And vice versa, when it is due time for this transformer, similarly, same situation is implemented. Next is condition monitoring devices, right? Okay, so I made mention of condition monitoring devices. Okay, so let's say for a high voltage switch breaker, right? We have condition monitoring devices that can monitor the purity of the SF6 gas, right? Intrusion of moisture, intrusion of contaminants. Okay, then also the gas pressure and the level of the gas pressure. We can also monitor basically the contact wear, the contact resistance, right? Then basically the travel motion of the contacts, right? So there are so many condition monitoring parameters that can be implemented on a high voltage circuit breaker. Similarly, there's also a lot of condition monitoring devices that can be installed on a power transformer. The first one is bushing monitoring devices that measures the capacitance, the power factor, and also leakage current in the wattage loss. You can also install a dissolved gas analysis. We have the 2 gas, the 5 gas, the 7 gas, and the 9 gas, right? And in addition, it can measure the moisture level, right? Then we can also have OLTC condition monitoring that basically measures the contact wear, the amount of current being drawn by the motor, then also the motor torque, right? Then also the contact resistance, right? It can also measure the dynamic contact resistance. Same applies to a breaker, right? Dynamic contact resistance, basically, it measures the amount of resistance as you open the breaker contacts, right? So that is a dynamic resistance, right? So these are some of the condition monitoring devices that you can install on this substation device. Another condition monitoring devices that you can install on a medium voltage switchgear is a condition monitoring device that can basically monitor PD activity, humidity, temperature, right? Then also, you can have a condition monitoring device for a battery system, right? Okay, so you can measure the individual cell voltage, you can measure the connection resistance, right? Then you can measure the overall battery DC voltage, right? Okay. So if you have all these condition monitoring devices, then that will help you to basically, because it's going to give you real-time data, right? For you to know that your condition of the equipment and be able to extend the life of their maintenance strategy to an example of selecting a condition-based maintenance strategy for that. Okay. Now let's talk about the types of maintenance that we have. We have planned maintenance and unplanned maintenance, right? Then under planned maintenance, there it is basically categorized into different maintenance strategies. Then unplanned maintenance, it is also basically broken down into different maintenance strategies. Now let's take a deep dive into the different maintenance strategies that we can have under planned maintenance, right? Okay, so now we're talking about planned, right? So the first one is predictive maintenance. Predictive maintenance. Okay, so as the word speaks for itself, right? It says predictive, right? I'm predicting based on the algorithm that I have, having learned something, right? Okay, so what are the predictive maintenance tools out there? The first one is infrared thermography, right? Thermography, right? So I can utilize infrared thermography on power transformer, right? To basically determine the hotspots, right? I'm determining the hotspots to determine the ambient, the degree temperature rise above ambient, or the temperature rise in between phases of, let's say, phase A, phase B, phase C, to determine the action that I need to take. Okay, so I can also use infrared thermography to determine if there is a good flow of oil through the radiator. Also, I can use it to determine hotspots inside the tank of the power transformer. Right. Then also another predictive maintenance tool that I can use for the power transformer is DGA analysis, right? Real-time DGA analysis that basically samples oil, analyzes and spits out all the gas and components, right? Carbon dioxide, carbon monoxide, hydrogen, acetylene, ethylene, ethane, right? And also oil quality, right? Moisture level. Then also for motors, you can also have vibration. Vibration is also another predictive maintenance tool that you can utilize, right? Vibration monitoring to basically collecting the vibration data and be able to determine the condition of the transformer, right? So these are the various predictive maintenance tools that are out there for substation and generation assets, right? So let me emphasize it again. The first one is infrared thermography. The second one is DGA and moisture level. The third one is vibration for motors, right? Then for the infrared thermography, you can also utilize it for power transformers to determine the efficiency of cooling in the radiator. You can also use it to determine hotspots for your connections inside the transformer and also for your bushing connections to the external transmission system. Next is run to failure, right? Run to failure is usually implemented for assets that have a low criticality. That is basically, at the bottom of the classification level, right? Okay, so it means that they are not so important, equipment. So, for instance, if you have a motor that basically you can easily replace it, you can easily, you have a spare, let's say 2-3 spares that are out there, and even then you can always call a manufacturer to deliver that same size of motor, right, with the same nameplate within a day, right? Then basically you can select or basically determine to run the motor to failure. The caveat is it can be very costly, right? Sometimes, when you run into problems of replacing that motor, where basically you think that that motor is easily replaceable, and you call the manufacturer and the manufacturer says, okay, I don't have this motor anymore, but I can refer you to another one, and maybe they are not ready for you. So then you experience a downtime and basically loss of our productivity, right? Okay, so on the other hand, if you have to store a lot of, if you have to keep your inventory high for these motors, then that is also additional cost. Next is time-based maintenance. Okay, so time-based maintenance is basically based on a fixed cycle, right? Okay, so when I give you an example, it's for power transformers. Usually, the time-based maintenance is a 6-year cycle, right? High voltage circuit breaker is between 4 to 6 years. Then, so this one is called major maintenance, major outage, or major overhaul, right? Then you can have a minor one where basically every year you do a predictive maintenance, right? Or every 6 months you do a predictive maintenance where basically you do visual inspections and data collections and infrared thermography, right? Okay, so this is what we call time-based maintenance, where you have a fixed intervals and to do your maintenance. So the caveat about it is about 70% of the industry implements this type of maintenance, right? 70%, right? Then I'll say 20% performs run to failure. And I'll say about 10% it's all based on this. Okay, so the caveat about this is sometimes you end up performing maintenance on an asset when you are not supposed to, right? It's not necessary. Let me put it that way. So you end up basically wasting money on that asset, right? Because the condition of the equipment is good, right? And so you've already scheduled it. You've scheduled it and you have to do it, right? So you end up wasting all the resources, money, parts, and etc. on this equipment, right? Rather you could have utilized condition-based maintenance to extend the maintenance cycle from, let's say, 6 years to 9 years or 12 years, right? And save some money. One other thing that I need to make mention that sometimes even during time-based maintenance, that you don't need to do maintenance. You have to do intrusive maintenance. You end up causing damage to other components that will end up costing you more money. Next is corrective maintenance, right? Corrective maintenance, can occur on any day, right? Okay, let's say you have a failure of an equipment, malfunction of equipment, right? And you have to replace a component, right? Then basically corrective maintenance comes into play, right? And also, even during time-based maintenance, that you are performing time-based maintenance, then you can also perform corrective maintenance. Also, sometimes during predictive maintenance, if it becomes necessary to perform corrective maintenance, you can do that. An example is during predictive maintenance when you're doing a visual inspection and data collection, and you find a substation fan that has failed, right? Then you can perform corrective maintenance by replacing that substation fan that has failed. Next is condition monitoring. Condition monitoring, I gave you similar examples, right? Okay, where for a power transformer, you can have a bushing monitoring device mounted at the top of the bushing, right? That basically collects and spits out real-time data on the bushing capacitance, C1, C2 section, turn delta 2, right? And leakage current, and the voltage and the current that basically flows through the bushing. You can also have a DGA monitoring device, right? 2 gas, 5 gas, 7 gas, and 9 gas, and also moisture level. And the OLTC, you can also have a motor current, contact wear, contact resistance, and motor torque. So that is for power transformer. For circuit breakers, right, you can have a contact wear, contact resistance, timing test, timing of the breaker, then travel motion of the breaker. Then also you can have a SF6 gas, purity, right, moisture level, contamination level, pressure, and density. For battery systems, same thing. You can have a cell voltage, gravity, impedance, terminal to terminal contact resistance, overall DC battery voltage. And for medium voltage switchgear, right, you can also have a PD activity, moisture level, temperature. Okay. So these are, some of the condition monitoring devices that you can have, and also for a whole substation setup, you can also have a visual and thermal camera that can be installed at various strategic locations within the substation environment, right? Let's say based on the size of the substation, you can have let's take an example for a bigger substation. You can have between 5 to 10 visual and thermal camera that basically will be assigned at different locations and different angles, and will be providing hot spots temperature for various equipment connections, right? So that is a typical example of condition monitoring, right? And I explained the advantages of condition monitoring, where basically it helps to reduce operation and maintenance costs, and also helps you to transition into condition-based maintenance from time-based maintenance, and basically helps you to extend the life of useful life of the equipment. Next is our reliability-centered maintenance, right? Okay, so reliability-centered maintenance is the optimization of all these maintenance strategies that I did mention, right? Based on criticality, the condition of the equipment, consequence of failure, environmental, safety. So that is what they call our reliability-centered maintenance. Then another maintenance strategy is unplanned, and that is emergency maintenance. Okay, so that is when you have a sudden failure, sudden trip of an equipment. So let's take an example. If you should have a through fault through a transformer, you already know what a through fault, right? If we have a high voltage source, and the low voltage terminal of a transformer, right? Okay, if you should have a fault here, what happens? Fault is going to go through the transformer from the high voltage side and from the utility source onto the faulted point, right? Okay, so when you have that, what will the circuit breaker do? The circuit breaker, the relay, the protective relay, either the differential relay or the backup 5051 relay will, or maybe the solid pressure relay will be the one that will trip the power transformer and take it out of service by tricking both the high voltage side and the low voltage side to take the transformer out of service, right? Okay, so when you do that, then you have to perform emergency maintenance inspection and testing on the power transformer. So with that comes to the end of my presentation, and thank you so much for your listening ears. And don't forget, if you like my presentation, to select the like button at my YouTube, and also don't forget to subscribe. And I think the first slide I indicated my YouTube channel, where you can take a look at it and basically have a lot of presentations out there that you can utilize for your career enhancement and also for your learning curve for your career. With that comes to the end of my presentation, and look out for my next presentation. Thank you.